The first figure today is happy birthday. Simple actually, it's a fraction. Was two prices the Minister of Evolution of Mathematical Society. So that was the prize for young mathematicians, and the prize in the honor of Kazimierz Kurakowski, that is administered jointly by the Polish Mathematical Society and the Institute of Mathematical Polish Academy of Sciences. So now, before the outlet the screen.
Thank you very much. Thanks for this introduction. And good morning, everybody. I'm really happy to be here. I always like these kind of talks where you're not supposed to speak purely about your research, but also try to make a bigger picture. And today I would like to tell you a few words about non-local PDEs and potential theory. So this will be mostly about non-local operators, and potential theory will appear somehow in the background. And of course, as I'm at heart a probabilist, there will be probability somewhere behind. Most of you surely know about regular ordinary differential equations. I'll give you two examples. One of them is radioactive decay. Let's see if it works. So in radioactive decay, the derivative is proportional to the function itself. The function describes the amount of radioactive particles, for example, and the number of radioactive particles decays in time. And of course, we all know the solution looks like that. It's not very essential for this talk. Just to give you some examples, and another maybe a little bit more interesting ODE is the problem of catenary. You hang a rope at two fixed points, and you want to ask what is the shape of that rope. And if you do carefully the analysis of physics, you arrive at the differential equation of that form, and the answer is given by the hyperbolic cosine. And so these are kind of classical problems that you learn on calculus class, probably. And then you learn about partial differential equations, which are, in the sense, very similar in flavor, but there are more variables here. So there are more derivatives as well. The derivatives in various directions, maybe a time variable as well. And a very simple example, a very classical example, is given by Coulomb's law, which turns into Poisson equation in mathematical terms, which is written here. It's the Laplace operator applied to an unknown function u is equal to a given function rho. So in physics, rho corresponds to the electric charge, and this is a known quantity, at least in this problem. And u is the electric potential, the gradient of which describes the electric force. And this triangle, the Laplace operator, as I've heard you already know, is just the sum of the second of the derivatives of u respect all spatial variables. Okay. What I like about the Wikipedia is that it has really some really nice illustrations. So that's a picture that illustrates the electric force on Wikipedia, and every talk must have a picture of a cat. So I'm done already, right? I mean, you can check
Przepraszam.
it out. Yes?
We don't see slides online.
Okay, maybe someone posts screen sharing. Let me see. Can you see the slides It's now.
Now, yes, thank you.
Okay. I think everything is fine. Recording is on, and the screen sharing is on. Yeah, somebody posts screen sharing at some point. Okay, thank you for bringing this up. Hope everything will be okay now. So this is essentially the first slide. Now let me show up the first for your reference, if you like. So here are the two ODEs that I described and didn't even read them out loud, but have a look at it. I'll post the slides online as well later, so you can check it if you like. But this talk is not about partial differential equations in this sense. This is about non-local partial differential equations, non-local PDEs. Well, ODEs and PDEs, the differential objects, describe what is called the local behavior of various phenomena, various objects. But often you encounter things that behave non-locally. And here are some examples. For example, if you have a system with memory, then the evolution of that system is described not only by the present state, but also by what happened in the past. So the operator that describes the behavior of the system must look into the past, which means it's non-local in time. There are also many examples of real-life problems where you have non-locality in space. For example, in physics, when you have two kinds of diffusions, just as in yesterday's talk, one of which is very fast and the other one's slow, then you can approximate the fast diffusion by a non-local interaction. So you can kind of think that the fast diffusion happens immediately, which means that two distant points can interact immediately with no delay. That corresponds to non-local behavior, non-local equation, or non-local operator. In various other disciplines like material science, things like propagation of stress in materials are also described by non-local objects. In biology, various models like population models also include non-local interactions, like animals moving very fast from one place to another, and otherwise behaving in a more local manner. So these are applications in other disciplines of science, but there are also important applications in mathematics itself. So non-local operators appear naturally in various disciplines like harmonic analysis, and also in probability theory, which is very close to my heart, and probability theory will show up in this talk later as well. So non-local operators became popular over the last decades. This is the plot of Google n-grams for phrases. As you can see, the spelling switched from non-local written single word to non-local written with a hyphen. But otherwise, the interest in non-local operators is ever growing. And you can also see this on data from Scopus about the number of research papers which have non-local operator equation in its title or abstract. So that's an ever-growing business, especially over the last decade. And there are various types of non-local operators. In this talk, I would like to focus on a particular class, which is sometimes called Levy operators. And they are particularly simple and in some sense easy to handle, yet they still lead to interesting and sometimes very challenging problems. So what is a non-local operator in this talk? Well, think of some quantity which is described by a function u, and that quantity evolves in time, for example, and the evolution is non-local in the sense that the values at the given point x, y, z change according not only to what happens in the arbitrary small neighborhood of that point, but also they're influenced by the distant behavior. So that you need to really know the value of u at every single point in order to tell how will that value evolve. So you can think this is the fraction of sick individuals and the pandemic is spreading, and you want to see how far it will go and how fast other individuals will become infected. And there is an interaction between distant points. The interaction between 2 points is described by a non-local kernel k. Okay, and we assume that this kernel k is translation. So it only depends on the distance between the 2 points and the direction of the 2 points. But if you move your space a little bit left, right, it make any difference. Okay, and of course this notation is very clumsy, so we use simpler notation where you integrate over Rn and you don't use coordinates. You just write the x for a point in Rn, and actually you don't need to work in R3. It works in the space of any dimension. Actually, it can be made much more general, that we're satisfied with working in Euclidean spaces. Okay, so this will be our standing notation. L will denote a non-local operator, which is given by an integral over Rn. The integral has a non-local kernel k, which is translation invariant, so it only depends on x prime minus x. And the integrand is just the difference of u at point x prime and x. All right. Now we'll assume make a few assumptions about non-local kernel k. First of all, we'll assume that k is non-negative, which kind of means that things tend to evolve to a stable state. That's the philosophy behind that. And if you in PDE business, that corresponds to working with elliptic operators. Of course, this is not only possible solution, but that's for today's talk, that's the discussion. Now we need some condition on k so that the operator L is well defined. So in order to have this integral well defined, well, you can assume that k is simply integrable. Then if u is bound, then the integral is well defined and the operator is perfectly well defined. Well, that's not what really shows up in applications, but that's a good start. If you assume that u is differentiable, then that integrand behaves locally as x prime minus x. So you can make k more singular. So in fact, you can require only that k is integrable at infinity and k multiplied by mod x is integrable near 0. So that works for smooth functions, well, differentiable functions u. And that's still not enough. In fact, what you want to work with is an even more general case where you only assume integrability of k locally with respect to x squared. So you can allow k to be more singular in the origin. Examples will follow on the next slide. And in this case, this integral is not well defined. It's a divergent integral here. But you can make it convergent by adding, say, a principal value here, which means that you integrate outside a small neighborhood of x, and then you pass the limit as the neighborhood shrinks to 0. Or you can do some other kinds of compensation, and this is just a matter of your personal preference, which way to go, which way you choose to go. But in this talk, well, I will not get into much details, and I will not prove things with that definition. So let's just stick to this intuition. All right. We will make one more assumption, just technical assumption, assumed in this talk for simplicity. So we'll assume that the kernel k is symmetric. So if point x affects point y and at some rate, then point y affects point x at the same rate. This is completely irrelevant for the results, except that the formulation in the general case is a little bit more complicated. I'll mention that briefly. So this is just for simplicity, and that will make the presentation much easier to follow, I hope. All right, so let me give two examples. The first one is a very simple one where you take the kernel k to be equal to 1 in the ball and 0 outside. So what does operator L effectively do? Well, it integrates u over a small ball centered at x and compares that value with the value at u, with the value of u at x. So this tells you how much different is the average in a small neighborhood from the value at the center of that neighborhood. Okay, well, it's a fairly simple operator if you scale it appropriately. So you change 1 into a thing that depends on the radius. Then you can easily show that as the radius goes to 0, so shrink the neighborhood down to 0, then that operator converges to a class operator. Well, that's fairly straightforward if you know the mean value property that we mentioned in the next slide. But even if you don't, then just use Taylor expansion, second order Taylor expansion, and see that the linear term cancels out. What's left is the second order term, and thanks to scaling, it converts precisely to what's in the second order term, which are the second order derivatives if you choose a constant appropriately, you get a constant 1, and you get just the Laplace operator. All right. Well, that's not the most important operator in applications. The important one in applications is where the introductions behave in a certain regular way, depending on the distance. So the most typical assumption is that the interaction speed decreases as the power of the distance. Okay, and the exponent here is written as n plus alpha, and alpha is necessarily between 0 and 2 because of our assumptions. So alpha needs to be positive because we want the kernel to be integrable at infinity. Well, you can relax this assumption, but it's not really very useful in applications. And the upper limit for alpha, the upper bound for alpha given by 2 is determined by the local behavior of the kernel. So you want this kernel to integrate x squared near the origin, which forces your alpha to be less than 2. And it turns out that if you take alpha closer and closer to 2, something interesting happens. If you choose the constant appropriately, you can again recover the Laplace operator. That kernel becomes too large so that the local term appears, and the constant goes to 0 necessarily, which means that the non-local part disappears, and in the limit you can recover the Laplace operator again. And in fact, this choice of kernel corresponds to what is called the fractional Laplacian. The fractional Laplace operator is already mentioned in the introduction, I thought. And that's an operator which is very close to my heart as well. I did a lot of research on it. And you can see that the interest in fractional Laplacian skyrocketed in early 2010s. And there is an ever-increasing number of papers on fractional Laplacian. For some reason, it became very popular in the PDE literature, but even before it appeared in other areas of science, but not mathematics. Yeah. You mean in what sense? You mean in the principal value? Oh, here. Well, if U is regular, then you can have pointwise convergence. Otherwise, you have L2 convergence, for example, and you can extend it to LPs. Actually, in any sense you like, given that U is assumed to satisfy certain things. That's fairly simple when you do the Fourier transform. So if you do the Fourier transform, you can see that the convergence in the L2 sense is absolutely straightforward. And otherwise, if you have some regularity view, you can assure any other convergence you like, really. Okay. And this is called a fractional Laplacian because if you understand it in the sense of spectral theory, for example, or the Fourier transform, then really the composition of that operator itself behaves like the power of the Laplace operator. Okay, I will not focus on that particular operator in my talk, but it's important to keep it in mind because that's probably the most important non-local operator in that business. And if you follow the numbers in these pictures correctly, you will see that there are more papers having fractional Laplacian in their title than those having non-local operators in their title. All right. In order to tell you something about this business, I would like to focus on one particular result, which is called Liouville's theorem. And I guess many of you know Liouville's theorem from their course in complex analysis, because this is one of the fundamental results about analytic functions. That's a theorem that tells you that the bounded entire function, entire means analytic or holomorphic in all of the complex plane, is necessarily constant. There's a key step when you prove the fundamental theorem of algebra that every polynomial has a root, and it also has other applications in complex analysis. Now, the real and imaginary part of a holomorphic function is a harmonic function, meaning that it satisfies the Laplace equation, the Laplacian of that function is equal to 0. And it turns out that if you assume that just the real part of your entire function is bounded, then it also implies that the function is constant. In other words, if you have a bounded harmonic function on the complex plane, it is necessarily constant. And that also works in higher dimensional spaces, in arbitrary dimension, really. And there's an even stronger version of that result, which tells you that you don't need a two-sided bound. It's perfectly sufficient to suppose that your function is bounded on one side. Since you can always set a constant, it's typically phrased as positive harmonic functions are constant. I think I have time to mention the proof of this result. That's a completely classical result, but I have a point in that. There are many ways to prove it. Actually, I think I've heard of at least 5 different proofs. But my favorite one uses mean value property. So harmonic functions are well known to satisfy the mean value property, meaning that the value at point x is equal to the average value in an arbitrary neighborhood of that x, I mean symmetrical, circular or Polish neighborhood. So if you integrate u over a ball centered at x and divide by the volume of the x, you will recover the value at the center. Once you have this property, the proof is actually one-liner. You just need to make a good picture. Okay, so you estimate the ratio of the value of u at 2 different points, called x and x prime, and use the mean value property for both of them, but with balls of different radii. So you pick the radii so that the ball centered at x is entirely contained in the ball centered at x prime, but the difference is not too large. The difference, say, is equal to the distance between these 2 points. So you write this as a mean value property. I mean, write u of x and u of x prime using the mean value property, and then you observe that the integral over the red ball is less than the integral over the larger ball because your function is positive. So this ratio is not greater than 1, which means that the ratio of u of x and x prime is not greater than this quantity. But now when r goes to infinity, when radius goes to infinity, this clearly converges to 1, which means that u of x is less than or equal to u of x prime. Now you can flip the role of x and x prime, and you get the value of u at x is equal to the value of u at x prime. Hence, u is constant. It's a very neat proof, and it shows you that the example that I gave you, which approximates the Laplace operator, it has some second meaning. I mean, it's not just a random example, it's really connected with the Laplace operator. And these non-local operators that we're studying here are kind of really generalizations of the Laplace operator. Okay? Now, a natural question arises whether there's a variant of Liouville's theorem for non-local operators. So instead of assuming that your function is harmonic, you assume that it is L harmonic with respect to our non-local operator L. So as you remember, L is assumed to be kind of elliptic non-local operator, and that's a natural guess that this Liouville's theorem also is also satisfied in this context. It's fairly natural to conjecture because, for example, if you think about the bounded U which has a global maximum at some point, then by definition, the value of L at that point is negative, which means it's non-zero. So any solution of that equation cannot have a global maximum inside the domain where it is defined, which kind of convinces you that it should be constant, right? Now, you don't assume really that it has a global minimum or global maximum by saying that U is positive, because go to the infimum at infinity, but that's a fairly natural conjecture, so to say. And it turns out that this has been studied by a number of people. In using a completely different language, this was already carried out by Marcel Ries in 1938. Ries proved essentially what is called Harnack's inequality for solutions of that equation in modern language. At that time, he spoke about fractional potentials, which are called Ries potentials. But essentially, this is the same result. This Ries paper is famous among the potential theory crowd, but it's not so well known among people outside of that discipline. And there are really many results given which have been reproved by the PDE community later with even more complicated methods. On the PDE side, this problem, without really assuming that U is positive for the fractional Laplacian, was studied by Chen, D'Ambrosio, and Lee, and independently by Mustafa Hall in 2015 and 2016. There were 2 lovely papers about that. And for more general operators L, but general. This also has a long history. I'll just give you a few names. Barlow, Bass, and Bui in 2000, Priola and Sosavczyk in 2004, again Fall and Weth in 2016, and also the true PDE people like Rosoton and Serra in 2016 wrote a paper where they also proved that kind of theorem. And there's a more recent paper from Francisco Kuhn from 2021, where this is proved for operators which are somehow similar to the fractional plus operator, but more general. And when you ask the question for general operators of that form, we say Levy operators, then there's a fantastic paper by Denis from 1959, where he studies the Newby case, where K is bounded, where the integral of K is bounded, this is finite. In this case, well, I mentioned that in the next slide, the problem is of a little bit different nature, and you can use somehow more standard potential theoretic methods. And when you consider the case where the integral of K is infinite, this is a more modern problem. A solution for bounded U, not bounded on one side, but bounded on both sides, was given 4 years ago in Paris, 5 years ago by Alibot, Leso, and Anderson. Their proof is very long and very technical.
Audio isn't recording. Just make sure the screen. Oh, is the recording still on? Recording? Yes. It is recording.
Yeah, it's recording. Let's go. Okay. Hello again, people on Zoom. I'm not sure how long did you lost me. So if you'd like me to repeat something or go back, let me know.
Oh, it's okay.
It's okay. All right. Okay. So I was discussing the paper by Alibot and Alain Jacobsen. The proof was greatly simplified 2 years later by Berger and Schilling, who actually did not know the result of the 4 autos that I mentioned before, so it's kind of done independently. And it was even improved in the forthcoming paper by the same 2 authors and Shankarotsky. They needed to assume actually less. They needed to assume some that U is positive and bounded from above by what is called a submultiplicative function, which integrates the kernel K. Well, I call it simply sub-exponential. That's not very rigorous, and I will not get into the details. And actually, together with Tomek Grzybny from the same department, we are able to improve that result, getting rid of any assumption and prove a completely general result. Indeed, every positive L harmonic function is necessarily constant as long as L is given by that expression. There are some hidden assumptions like that K is non-trivial. So, for example, it's not concentrated on proper subgroup or something like that. We allow K to be measured, but let's just keep things simple and consider K to be a positive function, when it's positive on some set of positive measures. All right. So let me make 2 remarks here. The first one is that, as I mentioned before, we do not really need to assume that K is symmetric. But if K is non-symmetric, there may be other positive harmonic functions. And it turns out that all of them are exponentials or averages of exponentials, integral mixtures of exponentials. So in this case, you can prove that every L-harmonic function is an integral of exponential functions with respect to some measure over a set of parameters for which these exponentials are indeed L-harmonic. So the formulation is not as nice as for symmetric, but the proof is virtually the same. So that's just a side remark for those of you who are interested in the general case. And another remark is why we care about this theorem. Well, actually, it turns out that there are at least two reasons to have a theorem like that. So Leibniz's theorem has been used in PDEs, not theorems, not local PDEs. First of all, to prove uniqueness of solutions. That's kind of obvious application. I mean, if you have uniqueness of solution with right-hand side equal to 0, then you can build up on that and prove uniqueness for more general cases where you have some nonlinearities involved. And another maybe less obvious application is to regularity theory. So what do PDE people often do is they consider a solution without assuming any regularity, and they want to prove a priori result, as they say, which would assert that every solution is automatically regular, say, Helder continuous with some exponent or something like that. And the standard way to do that is blow-up method, so you can zoom in around as a point where the solution would be too singular. And by zooming in, you approximate a solution of a linear equation to the right-hand side equal to a constant. You can put that constant to the right side, to the left side, and make it 0. And then you use Leibniz's theorem to deduce that you get absurd. You get that the solution is constant, even though you assume that it is not. Yep. Yep.
So I would like to understand how big is this set lambda? It is something like dimension 1 in Rn,
in a sense, yes. I mean, that depends on the operator L. That depends on the choice of K, right? So if you say have two-dimensional case, and you fix one direction, say that one, then along that line, of course, such an expression is given here. Of course, it's maybe too much, but it's easy to see that this expression is a convex function. So there are at most 2 points where this is 0. That's for a regular convex function. So it turns out that essentially that set lambda is necessarily a boundary of the convex set. So that's some convex set, and the set lambda is necessarily the boundary of that. I mean, it's contained in the boundary of that convex set.
So in particular, this neither mu is not a letter, neither about something.
No, mu can be an arbitrary measure. Yeah, so this is an arbitrary positive finite measure concentrated in that set. Then that set can be empty, really. It can be a single point, 0. Okay, in this formulation, always contains 0, so the picture is probably wrong. But in the more general situation, it can also be empty. There can be integrability issues here, which would make it not contain every boundary point of the set where this is negative. So there can be some subtle issues with the definition of that set, maybe, but otherwise, that's the result.
This form of solution really important since we have a flexibility to choose this measure mu differently than how much we learn about you.
Well, say in one dimension that tells you that this is kind of hyperbolic sine or cosine. I mean, the mixture of two exponentials. That does tell you something, right? I mean, you're perfectly satisfied with the solution to the catenary problem that is hyperbolic cosine, even though there are two parameters. So it's the same here, right? You have a number of parameters, which is not really surprising, and that tells you that all the solutions are given by that number of parameters. The number of parameters in some sense infinite because it's hidden in that measure, but well, otherwise, well, that's just a representation of the solution.
Okay, so the most important thing in this problem is this determination of the set lambda, not necessarily the The exact form of the measure mu, yes?
No, I wouldn't agree. I mean, that tells you, for example, that all solutions are convex, right? These are convex functions. That tells you that they are infinitely smooth with regular. That does provide you with. Well, I mean, you can choose your measure, which there's one correspondence between solutions and these measures. So for every measure will give you a solution, and every solution is of that form. That's like complete characterization of the class of solutions. In the non-symmetric case, there may be, I should make it clear maybe. In the non-symmetric case, there may be more solutions to that equation. It's like if you consider harmonic functions, well, the bounded ones are constant, but there are also affine functions, there are also harmonic polynomials. And of course, the answer is not as simple as in the case of positive harmonic functions, but it still tells you a lot about the structure of the space of harmonic functions. And it's similar here, except that here you do assume that they are positive, but the structure is still again more complicated. Yeah. Sure.
So in some sense, this is the form of the general solution, and it is parameterized by all possible measures.
Yeah, exactly.
Lambda is fixed.
Yeah.
Okay.
I mean, yeah.
Okay.
Yeah, the set lambda depends on the operator L, and then you can pick any measure on the set lambda and you get the solution. That's complete description of the class of solutions. Yeah, that's why I didn't really want to focus on that case, because I didn't want to get into the details. But actually, I'm very happy that you asked that question. All right. So I won't give you the proof of that theorem, but I'll give you I'll tell you about the methods that are used in the proof. So first, we need to discuss the Nice theorem about the Newbines case, right? And it's still very complicated, and actually, it's the most complicated part probably. So we assume that K is an integral kernel, and U is a function which is harmonic with respect to that operator L, which was given in the previous slide. And we want to prove that U is constant. So how the proof goes? Well, actually, it uses the abstract Choquet's theorem on convex cones. And the cone which is studied here is the cone of what is called superharmonic functions. So one considers functions which are not solutions of that equation, but instead they satisfy the inequality. The operator L applied to U is non-positive. And well, these are called either L superharmonic functions or excessive functions, depending on the source. And you can prove that this is a convex cone with a lattice property, so you can apply Choquet's theory to that. And if you that brings your problem to the question of identifying the extremal points in that convex cone, or the section of the cone really. And it's not so difficult to realize that the extremal points are either exponentials or what is called the potential kernel. But that's pretty demanding, and that belongs to what is called potential theory. That's taken from Wikipedia. Potential theory is precisely the study of harmonic or superharmonic functions. The classical one deals with classical harmonic functions, and then there's this general potential theory, which deals with extensions where you replace the Laplace operator by, for example, the class of non-local operators considered here. But it's in fact, it's even more general. All right, so that's the first place where potential theory shows up. And actually, it's much better if you think about that in probabilistic terms. So if the integral is not just finite, but if it's equal to 1, then you can consider a random walk. So just a sum, increasing sum, cumulative sums of IID random variables, which have distribution density given by K. And it turns out that this interpretation is very fruitful. We'll come back to that later. And we can rephrase the Deville's theorem in that framework as follows. Turns out that if you have a stationary distribution for that random walk, then it's necessarily constant. Well, the constant means uniform over all of Rn. It's not a probability distribution, it's an infinite distribution, but still you easily realize what does it mean that it's stationary. It means that after each step, if the particles are distributed again according to uniform distribution. And again, it's a very intuitive result, but not only that gives you an intuition into the formulation of the result, but it also kind of allows you to give probabilistic interpretation to the proof. And this has been done, this has been carried out very rigorously using the theory of martingales in, I think, the 60s or 70s. All right. So that was about the Denise theorem. It's there. But now let's talk about the general case. The strategy is very simple. So you want to reduce to the Newbin's case covered by the Denise theorem. So you'd like to show that your function is not only harmonic with respect to the original operator L, but also with respect to some other operator L, which would fit into Denise theorem. Okay? So recall the probabilistic interpretation. Let us assume that the kernel K integrates to 1, and we consider a random walk which has increments distributed according to a distribution of density K. Okay, so we have a family of random variables moving in Rn, and the equation Lu equal to 0 translates into the convolution of U and the kernel K is equal to U. So in probabilistic terms, you would write this as U evaluated at random point x plus capital X1. So you start your random process at x, and you see where it is after one step, and take the mean value of U with respect to that distribution. That mean value is equal to the value of U at x. So this is a replacement of the mean value property for harmonic functions. The harmonic functions have this mean value property where for x1 distributed uniformly over a ball. That's precisely the formulation of mean value property for classical harmonic functions. So that already tells you that if you start with a classical harmonic function, you could equally well consider a random walk distributed uniformly on the ball, with increments distributed uniformly on the ball, right? And you'd like to do a similar thing for arbitrary operator L, not necessarily satisfying that Newbin's condition. So in the general case, the operator L also stands behind a certain stochastic process, but this process is in continuous time. It's a random walk in continuous time, in a sense, which is called the Levy process. So the Levy process is an object which is not so complicated to define, but it's much more complicated to understand. But in principle, you can think that the increments of xt over small intervals of times are sequences of IID variables. And so the differential of xt is in some sense a family of IID increments, which are somehow related to the distribution given by that infinite distribution with density K. That's a very informal way to introduce Levy processes. I will not go into the details, but the path of the Levy process looks as here. It's very similar to a random walk, but you just have small clusters of points instead of single points in some sense. Okay, and now again, the equation Lu equal to 0 can be interpreted in probabilistic terms as follows. If you take the expectation of U evaluated at x plus capital Xt, so instead of x at time 1, you take x at time t, and then let t go to 0, then the derivative will be 0. And that can be made rigorous if you like, but I didn't do it. And that should tell you that indeed the expectation of U evaluated of x plus xt is the same as U of x, because if something has derivative 0, it's necessarily constant. Now, that requires some assumption on U that I will explain in a minute. But let me just say that once you have this, you just apply the Denise theorem. Oops. You just apply the Denise theorem to that equation, because something's fine. Yeah. No, doesn't work. Don't know, but never mind. Okay, so this equation here is of the same form as the equation here, and you just set t equal to 1, you get the same equation. And Denis equation actually works with that kind. The Denis theorem works with that kind of equations. So you can apply Denis theorem to deduce that u is constant. Once you have this upper implication, the problem with the upper implication is that while LU can be well defined, the expectation of u of x plus capital XT may be infinite. That happens if, for example, that kernel K is compactly supported. If it's concentrated on a ball, for example, like in the example that we considered before. Well, this is a finite mass case for which we could apply the Denis theorem directly. But let's think about the Levy process, the continuous time process with that kind of distribution. There's a non-zero probability that it will make an arbitrary number of jumps within any given time interval. So it can go as far as you like. So the distribution of xt in that case has unbounded support. And if u grows fast enough, then this expectation may fail to be finite. And an upper implication fails in this case, and you're doomed. So this is the approach taken by Becker and Schilling, and they struggled hard to overcome this difficulty, but they were unable to, as far as I talked with them. And with Tomek Grzybny, we figured out a way to improve that, which is as follows. So the key idea here is that instead of considering a fixed time t here, you consider a random time, what is called the first exit time. And that's something very fundamental to what is called a probabilistic potential theory. There's a probabilistic approach to potential theory. And that the first exit time is fundamental objects in that theory. So you consider the time, the random time, first time your random process exits a ball of fixed radius, the green ball here, right? So the location of the random process at the first exit time is that purple dot here, in this case. Okay, and it turns out that you can use what we call Dynkin's formula to prove the same equation as the one written here, but for the random time. And with that random time, turns out that you get rid of integrability problems. So the distribution of that random variable here, x evaluated at the first exit time, is not worse at infinity than the distribution k. It's kind of comparable with k. So as long as u is integrable with respect to k at infinity, this guy is also well defined. So you don't need any assumption on u on the kernel k in order to get this formula. Well, L is equal to 0, so the last part actually cancels out. Disappears, and you can use Denis theorem to that equation to conclude that u is constant. And that's essentially the proof. Of course, there's a number of technical difficulties, but that's how it proceeds. And the proof is much simpler. It actually, you can fit it 2 or 3 pages maybe, compared to, I think, 30 pages of calculation in the original proof by the PDE people that I mentioned before. Okay, and let me use the last 10 minutes on one more thing. I hope I've really convinced you that probabilistic potential theory is the right approach to certain problems in non-local PDEs. Actually, that probabilistic intuition is something that helps you a lot and allows you to find simpler ways to go about sometimes very complicated problems. But let me spend the last 10 minutes on a different subject. What about science solutions? The entire talk was about positive solutions to the equation LU equal to 0. But you could, of course, ask a natural question: what happens when you allow solutions to change sign? Well, for classical harmonic functions, they no longer need to be constant. I've already mentioned the harmonic polynomials, and there are actually many more functions. All of them are given by a certain power series. They are entire harmonic functions. In dimension 2, they are just real or imaginary parts of analytic functions, of entire functions. In higher dimensions, the description is a little bit more complicated, but you can still do something. What happens if you try to become non-local? Well, I've been asked that question by a number of people, and I kept telling them that it's a very simple problem that you can solve in one line. And I'll try to show you that one line, but involves a number of technical things. First of all, we'll need the Fourier transform. We'll just define in a very usual way for integrable functions, but we'll need to use it for modular objects, namely for tempered distributions. So I'm not going to tell you what the tempered distribution is, but it's a kind of generalized function, like measure or even something more general. And that's the distribution, and tempered distribution, an object of that kind which is suitable for doing the Fourier transformation. So you can think about signed measures and similar stuff, for which you can still define the Fourier transform in a certain way. Now, you can convolve functions and you can multiply functions, but that's not so simple with measures. I mean, measures still can be convolved, but you can't multiply two Dirac delta measures. That's just not well defined. And it's even worse when you try to multiply or convolve distributions. But it turns out that there is a notion of convolution or a multiplication of distribution. It's not always well defined, but you have criteria which tells when this is well defined and allows you to do some calculus with it. For example, you have what is called the exchange formula. Well, for functions, you probably know well that the Fourier transform of the convolution is just the product of Fourier transforms. The same is true for distributions. As long as the convolution of two distributions is well defined, the Fourier transform of that convolution is the product of the Fourier transforms of each of the factors, and the product is not also is again not the usual product because they are not functions, but these are distributions for which you can really define the product in a sort of natural way. Okay, once we have all these ingredients, the proof that every signed solution is, well, not necessarily maybe a constant, but say a polynomial, is pretty simple. So here's the proof. So you start with LU equal to 0. Let me see. Make this laser pointer work. No. Okay, it's started working. Thanks. All right, so we start with the equation LU equal to 0. Now, if you look at the equation, that's a convolution type equation. The operator L is translation invariant, the kernel K is translation invariant. So that really looks like a convolution equation, and you can really write it down as a convolution equation with with an object which is no longer a function, it's a distribution. But you can really define a tempered distribution capital lambda, such that that equation LU equal to 0 is equivalent to that convolution equation. Well, this is a convolution of distributions, so watch out, but otherwise it's perfectly fine. Now you can apply the Fourier transform to both sides, and you can use the exchange formula. So that tells you that the original equation is equivalent, or at least implies the equation of form the Fourier transform of that distribution lambda multiplied by the Fourier transform phi is equal to 0. But again, multiplication is something a little bit weird here. Nevertheless, you can, it's well known really, it's not very difficult to show that the Fourier transform of lambda is a nice function. It's a continuous function, a negative definite function, if you like, which can be 0 only at a single point at the origin. Otherwise, it's a continuous non-zero function. So you can divide by that function, right? You can divide by something non-zero and conclude that the Fourier transform of u is necessarily equal to 0, except possibly at the origin. Now, watch out, the Fourier transform of u is not necessarily a function, it may be a distribution. So it's a distribution which is supported at a single point. So it can be, for example, the Dirac delta measure, which is a Fourier transform of a constant. It can be the derivative of the Dirac delta measure, which corresponds to a linear function, and so on. More generally, distributions which are supported at the origin are Fourier transforms of polynomial. So you can conclude that U is a polynomial. Now, that's one liner. I mean, it's a long line. I actually used 2 lines for that. But it's a very simple proof, which you can actually make work. You can make it rigorous. For example, if your operator L is a Laplace operator. You can also make it work when the Fourier transform of the distribution lambda is a smooth function. if this is C infinity, this is a perfectly rigorous complete proof, which is more general than the proof for positive functions, because, well, here you consider science solutions. And I kept telling people that, well, you can do it along these lines. You just need to find a good reference for these product of distributions in the general case. Certainly people studied things like that. And at some point, a friend of mine asked me, okay, can I write the details? I started digging through the literature. I was unable to find a statement that would cover the situation we have here. And it turned out, in the end, that this is wrong. You can't divide by positive continuous functions when you multiply distributions. While dividing by a function is essentially multiplying by its inverse. So you can define the inverse of that function. Oh, again, something happened. You can define the inverse of the Fourier transform of capital lambda. And you can multiply by it. But the product of distributions is not associative in general. So you cannot cancel out these terms. And I thought this was only a technical obstacle, but it turned out that it is not. That you can really sit down and construct a counterexample. And this is last slide, last minute. There are two counterexamples written here. So the first one is that one that I've already mentioned to you, that you can construct a continuous everywhere positive function phi and a non-zero temperate distribution such that the product is well defined and zero, but none of these objects is zero. Okay? So there's no division in the world of distributions. That's a takeout message from this theorem. And you can really make these objects related to what you're interested in. So you can kind of do the inverse Fourier transform and work a little bit harder to find a non-local operator L of the form that I just listed before, this was given above. And a smooth non-zero function U, which is harmonic, which is a solution of LU equal to 0 everywhere, but which is not a polynomial. Actually, it grows very slowly. It's not bounded. We know that it cannot be bounded. It cannot be even bounded on one side. It does grow, but it grows very slowly, slower than any polynomial, for example, slower than any power function greater than 1. And that was very, very surprising for me. And that broke down the strategy of the proof. Well, it's not that bad. We also have some positive results using some algebras of distributions where the product is indeed associative. But the general proof strategy like that just cannot work, which is a big surprise to me. Okay, my time is up. Thank you very much for your attention. And questions I would have to answer.
Question?
Hello. I wanted to ask, I'm a bit confused. So why, what assumption are we making to think that there should be a polynomial? I mean, you just showed that it's not true, but why should there be a polynomial type solution for this type of equation? I mean, for example, I think of the Laplacian. The Laplacian of something is 0, it being equal to 0, not mean that's polynomial.
Well, okay, we assume that things are temperate distributions here, which means they do not grow too fast. The growth is controlled by some polynomial. So essentially, this proof for the Laplace operator tells you that every harmonic function which is bounded by a polynomial, which grows no faster than some polynomial, is necessarily a harmonic polynomial.
Okay.
And sorry?
Like Cauchy bounds.
Yeah, something like that. Exactly. And that's what you expect, and what actually is true for many other situations, like for the fractional Laplace operator. This also works, and for the fractional, in the non-local case, you often have these tempered, polynomial bound for your solution by the sole integrability condition. You want to have LU well defined, and if the kernel decays like a polynomial, then your solution needs to be bounded by the polynomial as well, which kind of automatically tells you that your solution is a temperate distribution. So this is a really good setting for the non-local problems. For the Laplace operator, it's not completely satisfactory, but it's also, I think it's called sometimes strong Liouville's theorem. you have a solution which is bounded by a polynomial, even one side really, then it's necessarily a harmonic polynomial.
Okay, that's it. Thank you.
If we have alpha equal to 1, so we have minus Laplace and 1/2, it's a fermionic language in which normally square root of Laplace is something fermionic. We don't have any fermionic language.
I'm not sure what fermionic means.
For example, Dirac operator, the square of a Laplacian in 4 dimensions. Yes, because square gives you Laplacian. So if there are a fermionic language for which one can see what are the, I don't know, results for alpha equal to 1 in the fermionic, in the anti-commutative variables language. Always see that square root of Laplacian is fermionic.
Okay, so
is square equal to no.
yeah, I know what you mean. So there are some relations with okay, I won't use the word fermionic because I don't really understand what it means. But indeed, there is some connection with, say, Schrödinger, like.
Is alpha one distinct?
Well, in some sense, yes. Sometimes you can come up with some explicit expressions and things like that. But in this context, it is not free. I mean, what I wanted to say is that there are some relations with say, basic equations of quantum physics, like the Schrödinger equation and so on, which are related with the square root of Laplacian, often with an extra constant term on the square root. But I don't think it has really any real-life physical meaning. It has been used by, for example, Lieb to study the stability of matter, and that's how it became popular in the PDE literature in the 90s in some sense. But I don't think this is just an approximation to something that could be more closer to the true model. I don't think it has any true physical meaning as it is, really, if that answers your question. But yeah, I'll be happy to talk about that later.
The transform of a fermionic thing very well defined. Alpha equal to square root of 2 is something strange, but alpha equal to 1, so the power 1/2 corresponds to a very well defined physical thing, like a Dirac operator in 4 dimensions.
Okay, yeah.
So I think that the problem is that everything which you have discussed is scalar value. So the operator is no longer differential operator. So pseudo-differential operator, and the unique context appears the solution to define the square root of Laplacian, which is still differential operator. And the right to pay is to go into gamma matrices and bound with vector value, something vector value. But here everything is scalar value. So I would suspect that the answer would be negative.
Probably. I mean, I don't understand the question, so I can't really give them this answer. But I mean, certainly this is no longer differential. This is, as you said, pseudo-differential or non-local, depending on your point of view, which makes it non-physical in some sense. And for example, you can get Lorentz covariance here and things like that. So it doesn't really correspond to what you get with Dirac operator, for example, right?
Any other questions? Maybe the other ones, more question. What would be your kernel? It's just some it's right now in or time delays, you have a fixed time delay in the past. The kernel is some of the is it here or make no sense or?
I mean, here the kernel corresponds to spatial.
Okay, good. Yeah. Okay, so let's say it's just
Some 2 points.
In some 2 points.
Yeah.
Okay.
Then
Well, that's fairly. I mean, if it's 1 point, one direct delta, on the probability side, you get what is called a Poisson process, and that's fairly straightforward to write down things explicitly. When you have 2 direct deltas, you get convolution of 2 Poisson distributions. Probably, if you think about the semi-group, for example, generated by that operator. So you can really write down a lot of things explicitly, and probably a lot of things simplify as well.
okay. So time delays were not
No, yes. This was about actually time homogeneous solutions, which do not evolve in time really. When time delays are present, then things get really different. I mean, you use completely different techniques. This is no longer elliptic, for example. The question studied here makes little sense probably, but of course it has been studied. It has a lot of applications also, various physics and so on. That's not my part of that business, but yeah, if you like, we can also talk about that later maybe.
Thank you.
Maybe just one more question, but I'm afraid that this question will be a little bit technical. But if I have a dot operator, then I take some fractional power of it, and for you, I would like to take some function which is completely supported and smooth. Okay, something like modified like that. And if I have this fractional Laplacian, what happens with the support of this function after I apply this Laplacian? Is it the whole real line already, or?
Yeah, essentially yes.
For every power which is not an integer, yes?
Yes.
Immediately you have full support of the whole line, yes?
Yeah.
Okay. Okay, thank you.
Well, if there are no other questions or comments, then let's thank the speaker again. And hope you will keep going.